Okay. So, in our previous lecture, we arrived at Prandtl's boundary layer equation, which was balancing the advective acceleration with the cross stream diffusion of your horizontal momentum. So, these are our boundary layer equations. So, if you imagine I have a flow over a surface. So, I have this region close to the surface, which we found out scales as L by square root Reynolds, where Reynolds is defined as U infinity L by nu, where I have my boundary layer equations are the more appropriate equations to consider, whereas far away in the upstream region is where you solve your Euler or inviscid equations. So, what we said is in the bulk or in the region far away from the boundary layer, you are solving equation which is something like, if you say there is a stream which is accelerating, then this is your governing equation, which is your steady Euler's equation, where you have a pressure gradient that is balancing my acceleration. And the boundary layer equation tells us that we have dou p dou y is equal to 0, which means within the boundary layer. So, at a given x location, so if I say x equals to x star, p at x star is going to be a constant within the boundary layer. So, effectively what you will do is you solve the inviscid equations in the region far away from the boundary layer. You find what is your p infinity, and p at x star is going to be p infinity at x star. So, you have your outer solution. So, you have an outer solution here, and you have an inner solution, which is our boundary layer solution, which are going to communicate with each other. Now, this formally of doing the problem in two separate regions is known as method of matched asymptotic expansion. So, after Prandtl gave his boundary layer equations in 1904, 1905, after that a lot of development took place to formalize this, because Prandtl's equations that he derived was based on this insight that you should have the cross stream diffusion of your momentum present in the boundary layer balancing your acceleration. But to do this formally, when I say formally, what you are saying is you take your boundary layer solution, and the boundary layer solution in the limit of y going to infinity seen inside the boundary layer should become equal to your Euler or potential flow solution for y going to 0. So, here y is the coordinate which is basically the coordinate appearing from the solution in the bulk region, in the outer solution. So, you solve the outer problem and you let its coordinate go to 0, which means you are approaching the plate. Now, you know the inviscid problem will not be able to satisfy the no slip boundary condition. So, you are going to approach the plate and you find what is the limit of the inviscid solution as you approach the plate. This should be equal to the boundary layer solution which is near the plate as you take your y coordinate going to infinity. So, this is how you do this in a formal setting. So, you separate your problem. So, you have a small parameter here. The small parameter is inverse of Reynolds. This is actually the small parameter in the problem. So, when you do this in a formal manner, you arrive at the boundary layer equations and you apply the method of matched asymptotic expansion to connect the two solutions. So, What we will focus on is primarily working with Prandtl's boundary layer equation, which as I said, this is the leading order description. Obviously, we dropped terms that were present in the equation. If you remember, in the derivation that we had, we finally arrived at an equation which had a 1 by Reynolds term that was present, there was 1 by Reynolds square term that were present. So, all those terms were effectively dropped from the equation. So, this is the leading order description that you get for Reynolds going to infinity. So, now that we have this boundary layer equations, what we will try is we'll try to look at various kinds of flows and trying to understand how do we solve this for different scenarios. So, the first thing to understand with what is happening in the boundary layer is if you consider two scenarios. One is the inviscid scenario where we don't have a boundary layer, and the other one is the viscous scenario where you have a boundary layer. Now, if there is a plate, there is a horizontal plate with a uniform stream that is coming in with some velocity u infinity. If the flow was perfectly inviscid, that means there was no frictional effects in the flow, then this velocity would go over the plate, slide over the plate with no change in magnitude, because there is no friction. So, that uniform stream that is actually going over a flat plate doesn't experience any retardation. So, there is no retardation or slowing down of the inflow. When you have a boundary layer, this stream u infinity is going to get slowed down. We know that the moment it is at the plate, so this is a flat plate that I have here. The moment it arrives at the plate, it will come to rest. So, if you were to actually measure the velocity at some station that is further downstream, unlike the inviscid flow problem where the stream is completely unretarded, it remains exactly of the same magnitude, here the stream basically gets slowed down near the plate. So, this is the first thing that you would observe, that whenever there is a surface and there is a uniform flow that is moving past that surface, the fluid is going to get slowed down. So, there is a retardation or slowing down due to viscous effects, or precisely the no slip boundary condition. So, the fluid cannot slip over the surface. So, what happens to the fluid is it gets slowed down at the surface, and you would approach a velocity which is slower than the uniform stream when it is closer to the plate. Now, using this, we can actually try to think in terms of what would be the region where you have the boundary layer, because the boundary layer is not like a visible or an actual location in the flow. Boundary layer is basically what we are using to understand the region where viscous forces and inertial forces are comparable. So, we are defining our boundary layer as a location where viscous and inertial forces are going to be comparable. There is no physical boundary that is actually visible in the flow, where you would say that, okay, I can clearly see this is the boundary layer. Now, how do we then demarcate what is that region where viscous and inertial forces are actually being comparable? How do we actually identify that region? So, one way to do that, there are multiple ways of answering this question. One particular way of answering this question is if you look at the velocity profile in the viscous scenario. Now, if you look at the inviscid problem, if there was a fluid particle which was at a height y star, that fluid particle would continue to remain on that streamline, but more importantly, it would be on the streamline at the same height, because the streamline remains parallel to the surface. There is a uniform stream which is coming over a horizontal plate. The uniform stream remains unchanged. Because the uniform stream remains unchanged, which is why if there is a fluid parcel that was at a height y star at the inlet, it would also be at the height y star anywhere else further downstream. There will be no change, there will be no deflection to its motion. Now, what would happen to a similar fluid parcel? So, let me just sketch here. I have a similar fluid parcel which I have marked here at y star just when it has entered the plate. Should it remain on exactly the same height? Now, to see whether it remains exactly at the same height or not, we can first argue that let's assume that it remains at the same height. So, if it remains on the same height, that means it moves along a straight line. This is also y star. That means that the streamline which is entering continues to remain parallel to the bottom plate. I have a bottom plate that is along the x direction and this is my y coordinate. So, I am making a hypothesis that just like the inviscid problem, a streamline that I have started to sketch that is entering the plate continues to remain parallel to the plate forever. This is my hypothesis. Now, is that correct? So, let us check if that argument makes sense. So, the claim is, in the viscous scenario, a streamline for an incident uniform flow remains parallel to the horizontal plate. That is my claim. So, I have a plate, I have an incident flow of u infinity. I am saying if I now sketch one of these streamlines, it remains exactly at the same height, which is saying that it remains parallel to the plate. That is the claim. Now, we know that the velocity field, so let us say this is x equals 0, this is x equals x star. So, now we know that the velocity at a point further downstream is a different velocity profile. It has gotten slowed down. So, at x equals x star, I have a velocity profile where far away from the plate it is u infinity, but close to the plate it is a velocity where here the u at some y is smaller than u infinity. If this is x and this is y coordinate, then we know that due to the slowing down of the fluid will be moving at a speed that is less than the incident uniform flow. The fluid is moving over a plate, the plate is resisting it from moving, which means the fluid is going to get slowed down. As the fluid basically gets slowed down, you would actually have a velocity at any point away from the plate will always be smaller than u infinity. Only when you go infinitely far away would it approach u infinity. So, now I have drawn this red line which is making the claim that that red line is a streamline. This is my claim. The claim is this red line is a streamline and we have to check whether this claim is indeed correct. Now, if this is a streamline, what is the mass flux through this region? What is the amount of fluid that is passing through that region? It is a streamline. It will be 0 because we know the definition of a streamline is the flow is always tangential. which means if I draw, if the streamline is parallel to x axis along the y direction, there is no flow. V y on the streamline, I mean if you are using, so V is equal to 0 on the streamline if the streamline is parallel to x axis. So, m dot is equal to 0 on the streamline. There is no fluid that can leak in or out of that region. So, let us mark this region, we will call this as A, B, C and D. Now, what is m dot through the segment AD? AD is the plate is impermeable, there is no normal velocity through the plate, which means this is going to be 0. Then we have mass coming in from the left hand side and mass exiting from the right hand side. So, mass coming in from the left hand side is 0 to y star u infinity dy rho and whatever is the width coming out of the plane. This should be equal to rho times the width 0 to y star u of y dy. By mass conservation, whatever is coming in from the left should be whatever is going out from the right. But we know that uy is less than u infinity, which means these two integral cannot be equal. So, this equality is not possible. So, the claim that I made of the fact that a streamline for the incident flow remains parallel to the horizontal plate because I used my knowledge of the inviscid flow is not applicable here. So, what do you think would happen? If uy is less than u infinity, which means the fluid got slowed down, what should be the appropriate? So, I should have so if I draw the corrected streamline, whatever is coming in, if it has to be compensated by whatever is going out, this is what should be the streamline. This is now a streamline. Because you want the fluid that is exiting to carry the same amount of mass. So, if you consider the region between a streamline and the bottom plate, just choose any streamline in the flow that is basically entering from the left hand side and you trace out that streamline and you consider the region between that streamline and the bottom plate. Whatever is the mass of fluid that is present in the inlet between the streamline and the plate would exactly be the same amount of mass that is going to exit between the streamline and the plate at the outlet. Because at the streamline you will have m dot is equal to 0. That is the definition of a streamline. There is no normal flow across a streamline. A streamline by definition will always have velocity vectors being tangential to it, which means that you will not have any normal motion to the streamline. So, the amount of stuff that is entering from here will exactly be the amount of stuff that is exiting. So, this is our way of now trying to understand that what do we mean by the region where viscous forces are going to play a role. Okay. So, we will try to now actually compute that what would be our inference regarding the thickness of the boundary layer. So, what we will do next is use this idea that based on mass conservation, since the fluid got slowed down. See, you don't really need to know a lot regarding the equations here. All you need to know is that the fluid will get slowed down by the presence of a plate because of the no slip boundary condition. So, if I get slowed down, I need a motion of your streamline getting displaced up in order to accommodate the fact that I need to pump the same amount of fluid. You think of it in terms of a pipe. So, the moment you have a pipe where the inflow velocity is more than the outflow velocity, you know that the outflow cross section is larger than the inflow cross section. That's just the statement of mass conservation. So, you can think of this boundary layer as like this imaginary pipe, because the streamline on top is a no penetration boundary condition. The plate at the bottom is also a no penetration boundary condition. So, it is like a pipe or a channel which is basically diverging. So, it is diverging because the velocity as you go further downstream has slowed down due to viscous effects. That is the reason why the streamline is spreading out or fanning out. So, we will use all of this now to actually come up with measures of boundary layer. Like, how do we identify where is the boundary layer? Because as I said, the boundary layer is not like an actual region in the problem. It is basically our way of interpreting where viscous forces and inertial forces are going to be prominent. So, you can start by just giving some simple numbers. Simple numbers would be, you say the boundary layer is the location where it attains 99% of the free stream velocity. It is just an arbitrary quantity. So, you go here, you check what is the value of uy, and then you find the location where uy is equal to 0.99 times u infinity, and that particular y is your boundary layer thickness. So, this is delta 99 that would actually give you the location where the fluid velocity is almost become equal to the free stream velocity or the incident velocity. So, that is just a straightforward way of identifying. Now, you realize this is not a unique thing, right? You can come up with your own number, your own way of doing it. Another way of doing it is based on the picture that we have here displayed in terms of deflection of the streamline. So, we can then say that what is a boundary layer based on displacement of or deflection of streamlines. So, drawing our so I have an incident flow that is u infinity. I have a flow further downstream and so this is what we would get. We would get a deflection of your streamline. Now, if I say this height is h and here I write the height as h and then the deflection that has occurred I will call that as d star. sorry, delta star. So, delta star is the amount by which that streamline has gotten deflected from its inviscid location. If we were doing an inviscid theory, then obviously we would have had delta star actually being 0, right. So, let us apply mass conservation. So, mass conservation tells us that integral AB plus integral BD plus integral DC plus integral CA of rho V dot dA, considering this to be a steady flow with no sources and sink, should be equal to 0. If I just consider that particular region, I have these 4 boundaries in the problem, and if I integrate this and try to actually compute what is the amount of mass that is coming in, mass conservation just tells me what comes in should go out. It is a steady problem, there is no accumulation that is happening in the problem, there are no sources and sinks in the problem. So, in steady state this is what I should get. Now, of this, AB is an impermeable surface, CD is a streamline, right. So, V dot dA on AB is basically going to be V at AB, the vertical velocity at AB, right, dA on that. So, it is basically V dy. So, it is V dy on that particular surface on the bottom plate. Now, what is the vertical velocity on the bottom plate? 0. So, V dot dA on the bottom plate is identically 0 everywhere. There is no normal flow. Now, V dot dA on CD is the velocity component that is normal to the streamline. It is not necessarily just U or V. It is the component that is normal to the streamline. So, what would it be? Also 0, because of it being a streamline, whereas the first one is because of no penetration boundary condition. So, we do not have any contribution from AB, we do not have any contribution from CD, and we are now left with BD rho V dot dA plus CA rho V dot dA is equal to 0. Now, if we do it for the region we have, so rho I would take it outside, there is a width that is there which is coming out of the surface. V dot dA on BD is the velocity u, and dA is also pointing outward. So, it is u plus u dy with the integral going from h plus delta star. For the inflow, I will have rho w integral 0 to h, V dot dA, u is pointing towards plus x and dA is pointing towards minus x, which means this becomes minus u dy. You are looking at the normal to the surface, the outward normal to the surface. So, the outward normal to the surface on AC is basically pointing in the negative x direction, whereas the outward normal to surface BD is basically pointing in the positive x direction. So, this is just a statement of net inflow is equal to net outflow. So, you have in the inflow region, which is at AC, u is basically u infinity. So, I will have u infinity times h is equal to integral 0 to h plus delta star u dy. Maybe I'll just use here. Okay. So now if you choose your h large enough, then what you can assume safely that for y greater than h, u of y is approximately u infinity. So once you have chosen your h to basically be large enough, then your value for that you are going to get would be 0 to h u dy plus h to h plus delta star u dy, and if you choose your h to be large enough, you are going to get 0 to h u dy plus u infinity delta star. So we are almost there. We have now an expression which is u infinity delta star is equal to u infinity h minus 0 to h u dy. Now u infinity h, you can write it as u infinity 0 to h dy minus 0 to h u dy, which can further be written as 0 to h u infinity minus small u dy. So delta star is 0 to h 1 minus u by u infinity dy. Now what you can do is you can push h all the way to infinity, because h is just some choice that we have made initially. There is no special meaning to that value of h, it is some distance sufficiently far away from the plate. So now if I push h to infinity, I am basically going to get an expression which is 1 minus u by u infinity dy. So I have a measure of the boundary layer thickness which is based on the deficit in the streamwise flow at a given height. Because if this was inviscid, obviously this quantity would be 0, because u would be equal to u infinity at every y location. So when you look at this boundary layer here that it is forming, the consequence of the boundary layer is that the flow is gotten slowed down. So there is a certain slowing down of the fluid. Because the fluid has gotten slowed down, this leads to a certain deficit that is there in terms of your x momentum. So this deficit that you have in the x momentum is what is used in order to measure the boundary layer thickness. In other words, this boundary layer thickness is actually a measure of the displacement of your streamline. Because if there was no viscous retardation due to the plate, the fluid would have had streamlines continue remaining parallel to the bottom plate. There would have been no change. The fact that there is a viscous retardation is responsible for the fluid velocity to get slowed down from the incident flow, and thus the streamline gets pushed up. So the streamline is getting deflected or pushed up, and that is the reason why this is known as the displacement thickness. Sorry, limit will be 0 to, thank you, 0 to infinity. So you measure, so this is basically where it comes in terms of your experiments, or if you are doing some full numerical calculation, that you measure the fluid velocity in the x direction at a given point. You measure the streamwise velocity in the direction perpendicular to the plate. Once you have measurement of that velocity, you can compute this, and this will actually give you what would be the displacement thickness at a given x location. because this, if you remember, this is u as a function of y at a given x location. So, you are going to get the displacement thickness at different points in x by finding out how much has it slowed down. Now, this again is not the only way of doing it. So, we saw the 99% thickness criteria, we saw the displacement thickness definition. The other one is based on arguing that I have this slowing down of the flow has now gotten slowed down. By virtue of it getting slowed down, if I measure the mass flux through this region and I measure the mass flux through that BD region, they are going to be balanced, because that's the whole idea of that streamline being there. But what about the amount of momentum that is being carried out? Am I carrying out exactly the same amount of momentum that I am bringing in? Obviously, the streamlines get displaced. So, which means in that displaced streamline, we know that there is going to be a certain amount of deflection to accompany, to compensate for the fact that I have slowed down. So, I need to go through a larger cross-sectional region. But what about the amount of momentum that I brought in? Would that amount of momentum be the same just because I have now drawn that the mass is basically going to be conserved if the streamlines get displaced? So, let us measure the momentum inflow and outflow. So, the same configuration, I have an inlet which has a velocity u infinity. I have a velocity that slows down near the plate, and we now have an understanding of what the boundary layer is. So, there was an initial height at which we had a streamline sketched, and now we know that it gets displaced by an amount delta star. So, what is the inflow momentum in the problem? So, we had A, B, C and D. So, the amount of momentum that is entering, the momentum flux through region AB will be U rho V dot dA. That is the momentum flux that is entering through the region AB. The momentum flux that is exiting from region CD will be U rho V dot dA. Now, the question is, are they in balance? If I now say this is until height h and this is until height h plus delta star, would this basically be equal to 0? So, automatically, if this was indeed 0, which means the amount of momentum that came in was exactly the amount of momentum that was carried out through that region ABCD, that is basically saying that the plate that is present, which is responsible for the slowing down, is experiencing no force. Because if you look at this particular region that I have drawn, ABCD, if the amount of momentum that came in was exactly the momentum that was carried out and the problem was in steady state, that means there are no boundary effects of forces or surface forces acting in the problem. Influx of momentum is same as the efflux of momentum. That means there is nothing else that is there which would be applying any force. If I think of this as a control volume, in this control volume ABCD, if it is in steady state, if the boundaries are not applying any forces on this control volume, then influx is equal to efflux of momentum. That would be the statement. Now, we already have an intuition here that no, the plate is going to experience some force due to, it's basically trying to do work in slowing down the flow. So, it is going to experience some resistance or some force from the fluid. So, these two cannot be equal. So, let us try to actually find out what is the difference between the two. So, we will do them individually. So, let us compute through AB rho u v dot dA. Now, this is 0 to h, rho u is u infinity and v dot dA is minus u infinity dy. Minus because the normal to the surface AB is an outward normal that is in the negative x direction. For surface CD, I do the same exercise and I have 0 h plus delta star rho u and v dot dA will be plus u dy. So, this is rho u square dy, rho u square dy 0 to h plus rho u square dy from h to h plus delta star. Once again, we are going to say that h is large enough such that the fluid velocity at CD beyond h can be approximated as u infinity. So, we will go back to this integral at CD and write it as 0 to h rho u square dy plus rho u infinity square delta star. So, the inflow of momentum, which is minus rho u infinity square h. So, I have an influx of momentum, I have an efflux of momentum, and now the question is, what is the difference between the two? How much are the two actually differing? Because if I were to add the two, if they give me 0, that means there is no other surface forces in the problem. So, what I will do is I will basically look at the sum of these two quantities. So, looking at AB plus CD rho u v dot dA gives me rho u infinity square delta star minus h plus 0 to h rho u square dy. Now, just like before, we are going to push h before we write this out, I mean choose a limit of h. We have this expression, I can write it as rho u infinity square delta star plus rho 0 to h u square minus u infinity square dy, right. This particular term rho infinity square h, I can basically write it as rho infinity square 0 to h dy. So, what I have here now is rho u infinity square delta star, I will take a negative sign outside, u infinity square 1 minus u square by u infinity square dy. So, that is basically what I have now for my difference in the influx and the efflux of momentum. Now, if I substitute for delta star, we know what is delta star. So, delta star is u infinity square 0 to h 1 minus u by u infinity dy minus rho u infinity square 0 to h 1 minus u square by u infinity square dy. And I will push h to infinity in both cases. So, I will write this as the integral being from infinity. So, I have rho u infinity square 0 to infinity 1 minus u by u infinity minus 1 plus u square by u infinity square dy. So, what I have done is I have substituted for the expression for the displacement thickness, and by doing so, I now have an expression which is, if I write this out, u infinity square, the minus sign 0 to infinity u by u infinity minus u square by u infinity square dy. So, finally, what we have here is AB plus CD rho u v dot dA is equal to minus rho u infinity square integral 0 to infinity. I will take u by u infinity outside, so that gives me an expression of what is the loss of momentum, because if this was identically 0, then it just tells me whatever is the momentum coming in is exactly the momentum that is exiting. So, that loss of momentum, these are all somewhere there is a width that is there. So, everything here is per unit width. In the dA, I have written it is in terms of per unit width. There is a W that you can multiply throughout in order to get this in terms of. So, this is per unit width, what is the loss in momentum. So, the loss that is there per unit momentum, you can write it as in terms of dimensions rho u infinity square times some thickness as, so the negative sign tells you there is a loss in terms of what has come in terms of what has gone out. Clearly, you are pumped in more momentum than what has actually exited. So, there is now another way of measuring what is the boundary layer thickness in terms of the loss of momentum. So, this is known as momentum thickness. So, we have arrived at this by arguing that the momentum thickness is basically a length scale or the boundary layer thickness measure which gives me the compensatory loss of momentum, or in terms of this is going to also give me a measure of that how much of the fact that I have this boundary layer present in the problem, there is a flow over a surface, there is viscous resistance that is being offered. This viscous resistance leads to a loss, and I am quantifying this, the loss, in terms of the thickness. So, I am saying that if there is an equivalent, there is a u infinity flow that is coming in. So, rho u infinity square times a thickness or a length scale and times a width, this gives me the amount of loss in momentum flux that has happened. This has units of force, rho u infinity square as units of stress, and then theta times W has units of area. So, this gives me a force. So, what would be the equivalent thickness of a boundary layer that gives me whatever is the amount of momentum that I have lost by virtue of the plate being there. The presence of the plate has slowed down the fluid. By slowing down the fluid, there is a work that is being done in trying to move the fluid past the plate, and this work that is being done, I can quantify it in terms of a thickness, which is my momentum thickness. Now, you can carry this argument forward and do it for other kind of losses. We are not going through a full derivation once again, but you can now argue it in terms of an energy loss, and the energy loss based thickness will turn out to be of the following form. So, we saw displacement we first saw the 99% criteria for thickness, then we saw the displacement thickness, which gave us a measure of how much the streamlines were getting displaced, and we saw a momentum thickness which was based on the work being done to push the fluid past this no slip boundary, and then you can use that in terms of the loss in energy that is happening in the problem. So, the influx of energy and the outflux of energy will not, the kinetic energy that is coming in and the kinetic energy that is going out is not going to be in balance. That loss of energy can also be used to quantify what is the thickness of the boundary layer. So, these are indirect measures, these are not direct measures of what the thickness actually is. The displacement thickness gives you more of a physical, so if you were to put tracers in a boundary layer, you put dye in the boundary layer is steady, you would see the path taken by the dye would show a deflection, and that measure of deflection is in some sense related to your displacement thickness. But the other ones, the momentum thickness and energy thickness, will also be closely related. So, once you know what is the velocity profile, you can actually compute any of these things. So, there is no unique way of defining where the boundary layer is. You have to use some kind of a measure, whether the measure is deflection of streamlines, whether the measure is loss of momentum, whether the measure is just a brute force cutoff of velocity, saying 99% of free stream velocity is where the boundary layer is. You can use your choice. All of them will agree within an order 1 factor. They will not be vastly different. We will do some sample problems later and we will find each of these quantities for a given problem, and you will see they will be very close to each other. It is not like they will be widely separated, but these are ways by which you can get an understanding of what is the thickness of the boundary layer. So, the thickness of the boundary layer is tied with how the flow gets slowed down. What is the velocity profile at different stations? Once you measure the velocity profile at different stations, you will then be able to find out what would be the measure of different measures of boundary layer thickness. Okay. Thank you. So, with that I will close. Yeah.